This section deals with the reactions involving alkenes and alkynes and mostly focuses on reactions of alkenes. And there are two kinds of reactions typical of alkenes. The first one is addition reactions, and this is where two molecules combine or add together to give one new molecule, and we will look at several examples of that. And the other kind are redox. So if you remember from general chemistry, you would have discussed redox reactions or oxidation and reduction reactions. And it's important that you know that the two classes of reactions, both addition and redox, are not always mutually exclusive. Here's a slide that shows the general reaction that occurs during the addition process of a molecule to an alkene. What happens is you have a small molecule, AB, so this little tiny molecule here, and it reacts with the pi electrons of the double bond. Now, before we go any further, it's important that you know the difference between a sigma bond, and a pi bond. Basically, anytime you have one bond between two atoms, this is a sigma bond. And so this bond would be a sigma bond, this would be a sigma bond, this is, of course, a sigma, and of course, this is a sigma bond as well. This is also a sigma bond, okay? When you have a double bond, the first bond is always a sigma. So since I have a double bond here in my alkene, we'll put an arrow towards one of those bonds and we'll say it's a sigma bond. Any bond after the first bond is considered what we call a pi bond. And so it doesn't matter that I put the sigma bond on the left. I could have put it just as well on the right, but we'll say the second bond, this is a pi bond. And what's interesting is that pi bonds are weaker than sigma bonds, and therefore they have a greater propensity to react in an addition reaction. It's also important that you know that some addition reactions require what is known as a catalyst. And a catalyst is simply a species that is used to lower the activation energy of the reaction and thus increase the reaction rate. And you can also see here that when that pi bond breaks in the reaction, what I'm doing is I'm taking A and I'm adding that to one of the carbons, and then I take B and I add that to the other carbon. Now, there are three types of addition reactions that we are interested in. The first one is what we call a symmetrical addition reaction, and this is where we add the same atom to each carbon. So you know in the previous slide how I had A and B, it would be like A and A or B and B. And the two examples of this would be hydrogenation. This means we're adding hydrogen across the double bond, and hydrogen, of course, is a diatomic element, and you should have those memorized. And when hydrogenation is performed, you need a catalyst, and the catalyst can be either platinum, palladium, or nickel. Any one of those three will work equally well for a hydrogenation catalyst. The second type of symmetrical addition is what we call halogenation. And halogenation can be effected using either bromine or chlorine. And of course, bromine and chlorine are both halogens and are both diatomic elements. You might be wondering about fluorine or iodine, and these do not work. The reason why is because fluorine actually reacts too violently, so we get things like fires and explosions, which are generally things we like to avoid in the lab, and then iodination is too slow to be useful. Next, we have unsymmetrical additions. This is where we add hydrogen and another atom to the two carbons. The two examples we're interested in this class are hydrohalogenation. This is where we add a hydrogen and a chlorine or a hydrogen and a bromine, and we do that using HCl or HBr. And next, hydration. And this is where we use water, because hydration is simply adding water, but that requires a strong acid catalyst. And some possible strong acid catalysts would be hydronium, sulfuric acid, or phosphoric acid. And then last, we'll look at self-addition or polymerization. Let's start by looking at hydrogenation, which again is the addition of hydrogen. Hydrogen, again, is a diatomic element. So we take our alkene and we react it with hydrogen. And I told you, you have to have a catalyst. And the possible catalysts that you can use are platinum, palladium, or nickel. Either one is fine. But not only do you have to have a catalyst, palladium, platinum, or nickel, you also have to apply heat or pressure, either one, to the alkene and to the hydrogen in order to get the hydrogen to add to the alkene. So what happens during the process? The double bond or the pi bond is broken and we end up getting two new carbon-hydrogen bonds. Something that I'll add to hydrogenation is that when you're doing hydrogenations, you have to be very careful because hydrogen is a highly flammable and explosive gas. Next, we'll look at halogenation or the addition of X2. And of course, X2 can be chlorine or bromine. I told you that it cannot be fluorine or iodine. So what happens here is very similar to what we saw in hydrogenation, although we do not need a catalyst. So what happens is we react our alkene with our halogen. Here they've drawn the X2 as a Lewis structure like this. Again, it could be chlorine or bromine. And what's going to happen is we're going to end up breaking the pi bond and we're going to form two new sigma bonds between carbon and the halogen. Again, just to reiterate, because these are the things you have to know, the reaction occurs quite readily without any catalyst, so no palladium, platinum, or nickel required. That is only for hydrogenation. And again, chlorine and bromine are most often the halogen added. This is kind of an interesting figure that comes straight out of our textbook. It says here that the beaker on the left contains bromine, but no unsaturated hydrocarbons. So all that means that inside this beaker here, we have bromine, Br2, and bromine exists as a liquid. Now this is probably a solution of bromine because it's got kind of an orangey color, but if you had pure bromine, it's actually a deep, dark red liquid. So in this beaker on the left, we have some bromine. So it has a red color, right? It's red. Now what's happening is that in this bottle, so this is a bottle of gas and they have a regulator right here so they can regulate the amount of gas coming out of that bottle. What's in that gas container is ethylene gas, right? C2H4. And what does C2H4 have? It has a unit of unsaturation, right? It has a pi bond. So what's happening in this reaction is in this beaker, there was bromine, but they added the alkene to it. And so I've written the reaction up here. So we have our gas, our ethylene gas, and we're adding bromine to that, which is red. But what happens is the reason the beaker becomes colorless is because the product is an unsaturated hydrocarbon, which is colorless. Next, we have hydration, and I think it's pretty evident that hydration would mean the addition of water across an alkene or to an alkene. It says here that a water molecule can be added to an alkene. The addition of a water molecule to an alkene is called hydration. And in order to do that, we need a strong acid. And you can see that above the reaction arrow here, they just wrote H+. And what that means is that H+ could mean sulfuric acid, it could represent hydronium, and it could represent phosphoric acid, as we said earlier. It could also be other acids. And what's the definition of an acid? An acid is a proton donor, and that's why it's okay to just write H+ above our reaction arrow. And what happens is we convert that alkene into an alcohol. And now you see why it was important to memorize functional groups. Now in terms of the bonds, just like we saw in hydrogenation and halogenation, we're going to break that pi bond and we're going to form two new sigma bonds. One of them will be to the hydrogen atom, this one here, and one of them will be to the hydroxyl to form the alcohol. This slide just shows a quick summary of what we've just looked at. So if we take an alkene like cyclohexene, what's happening or what's in common with all of these addition reactions? In all of them, we end up breaking the pi bond. It gets broken, and then we form two new single bonds. Whether we're doing hydrogenation, we form two new single bonds to hydrogen. If we're doing halogenation, we form two new single bonds to halogens, and those halogens could be chlorine or bromine, not fluorine or iodine. If we're doing hydrohalogenation, we form one single bond to a hydrogen atom and one single bond to a halogen. Again, the halogens can be chlorine or bromine. And then finally, when we do hydration, we're adding water across that double bond. And so one of the single bonds is formed to a hydrogen atom, and the other one is formed to the hydroxyl to form an alcohol. Something that's really interesting is what we call unsymmetrical addition. If we take a look at propene or propylene, propene is the IUPAC name, propylene is the common name of this molecule. If I do a hydration of propene, I end up getting two different products. I form the major product, 2-propanol, and I form a minor product, 1-propanol. And the reason why I form two products is because the two carbons involved in that double bond are different. One of them has two bonds to hydrogen. The one that's labeled number 1 has two bonds to hydrogen, whereas the one that has the 2 above it has a bond to hydrogen and a bond to carbon. So these two carbons are different. And what that means is that they're going to react differently. And we'll look at that in more detail. But what's going to happen is the hydrogen is going to add to one of those carbons, and the other carbon is going to attach to the hydroxyl in the hydration reaction. And if I was doing hydrohalogenation, the other carbon is going to attach to a halogen. And so the question becomes, why is 2-propanol the major product, and why is 1-propanol the minor product? And the scientist who figured this out, why we get preferential addition of the hydroxyl to one carbon over the other, was named Dmitry Markovnikov. And he was a Russian scientist who studied the acid-catalyzed additions to many carbon-carbon double bond systems, so to many different alkenes. And what he noticed is that the majority of the hydrogen went to a specific end of the double bond, and he formulated an explanation for that. And his explanation resulted in what's known as Markovnikov's rule. And Markovnikov's rule is this: when an acid adds to a double bond, the hydrogen of the acid most often goes to the end of the double bond which had more hydrogens attached initially. Sometimes my students like to call this rule the rich get richer, which is just a way of saying the carbon that had more hydrogens initially is the carbon that preferentially will get the hydrogen. Now we're going to see that Markovnikov's rule works when we add water, if we're doing a hydration, and if we're doing a hydrohalogenation with HCl or HBr. So again, what you're going to see is that the hydrogen will always be added to the carbon which already had more hydrogens attached initially. Now let's get into the nitty-gritty of Markovnikov's rule by examining the propene molecule. So if we follow the rule, the rich get richer, we're going to add a hydrogen to one of these carbons, to either carbon 1 or carbon 2, and then we're going to add a hydroxyl to the other carbon. Now what's our rule? The rule is the rich get richer. So which one of these carbons has more hydrogens attached to it? Well, carbon number 1 has 2 hydrogens attached to it. And carbon number 2 only has 1 hydrogen attached to it. The other atom that it's attached to is a carbon. And when we're dealing with the rule, the rich get richer, it's in terms of hydrogens. Therefore, since carbon 1 has more hydrogens attached to it already, it is the carbon that will take on this hydrogen right here. And so, to draw the major product, let's start by drawing the skeleton, the carbon skeleton. The third carbon remains completely unchanged. But carbon number 1, first, it started out with 2 hydrogens in propene, and what we're going to do is we're going to add the other hydrogen to that. So now we'll have 3 hydrogen atoms, and carbon number 2 already had 1 hydrogen, and it's going to take on the hydroxyl. And so the major product, or based off of Markovnikov's rule, our major product is going to be 2-propanol. Now you might be wondering, well, could I get the reverse? Is Markovnikov's rule always obeyed? And the answer is no. Okay, this would be our major product. So if we did this reaction, this is what we would obtain in a higher yield, would be 2-propanol. But we will also get some 1-propanol as well. So let's practice drawing that out. So this doesn't follow the rich get richer rule. And we're going to put our hydroxyl over here like this. And so the minor product would be 1-propanol. It's very important that all organic chemistry students understand and are able to explain Markovnikov's rule. Again, Markovnikov's rule can be applied to hydrohalogenation. So it says here that an alkene can be combined with a hydrogen halide such as HBr or HCl, and the product is going to be what we call an alkyl halide. We looked at that in the functional groups video. And Markovnikov's rule, again, is going to be followed. So again, let's examine our alkene, propene. You can see the carbon that I have highlighted in red has more hydrogens attached. It has 2 hydrogens. The carbon that I'm highlighting in blue only has 1 hydrogen attached. And therefore, the major product is going to follow the rich get richer rule. And we end up with 2-bromopropane as our major product. We also get some of the minor product. Sometimes the major product is called the Markovnikov product. I'll just put Mark, so the Markovnikov product. And sometimes the minor product is called the anti-Markovnikov product. So I'll just put anti-Mark product. Hydration of an alkyne is a more complex process because the initial product is not stable and is rapidly isomerized. As you would expect, the product is an alcohol, but in this case, one in which the hydroxyl is bonded to one of the carbons of a carbon-carbon double bond. This type of molecule is called an enol because it is both an alkene and an alcohol. The enol is immediately isomerized into either an aldehyde or a ketone, as is shown in the reaction on the top here. And so when we add that water molecule across our alkyne, we only break one of the pi bonds, because remember, the first bond between the 2 carbon atoms is a sigma bond. Anything after a sigma bond is a pi bond. So that means that in an alkyne, the carbon-carbon triple bond is made up of 1 sigma bond and two pi bonds. So we'll put pi bonds. Now I only end up breaking one of those pi bonds when I add the water molecule across. So I end up with the alcohol on 1 carbon, and I end up with the hydrogen on the other carbon. And we call this an enol because we have an alkene and we have an alcohol. But what happens is that enol is not very stable, and it rapidly isomerizes or rearranges into an aldehyde or a ketone. Of course, if this R prime, if it is a hydrogen, it's an aldehyde, and if it's an alkyl or aryl group, I would have a ketone. Polymers are macromolecules composed of repeating structural units called monomers. A polymer may be made up of several thousand monomers. Many commercially important plastics and fibers are addition polymers made from alkenes or substituted alkenes. They are called addition polymers because they are made by sequential addition of the alkene monomer. The general formula for this addition reaction follows the reaction scheme that's shown down here on the bottom. We have our alkene monomer, and then we treat it with a catalyst and heat or pressure. And what happens is we end up breaking all of those pi bonds, and we form new sigma bonds to form our addition polymer. So let's say we took a monomer like styrene to make polystyrene. If we write out the formula the way that it was written in that scheme on the previous slide, I have my carbon-carbon double bond, I have a hydrogen, and then I have my benzene ring or my aromatic ring attached here. So what's going to happen is I'm going to treat this with a catalyst and heat or pressure, and I'm going to end up breaking all of these pi bonds and forming a polymer like this. So I'm just going to change my bonds to make them more like a tetrahedral bond. So I'll draw my benzene up here like this, okay? And since it's such a big molecule, a macromolecule we call it because it's so huge, because there's several thousand of these all linked together, I'll just write the monomer out a couple times like this, and then I'll put kind of bonds that end nowhere. And then I can simplify the structure with these square brackets like this, and I'll just put a subscript N, which means it's repeating over and over and over. For polystyrene that I have shown here in red, I can even shorten that to drawing a condensed structure where I only show one of the monomer units. So something that looks like this, I put it in a square bracket like this, because this is the monomer that's repeating over and over and over. And so what I have written in red or in blue, both of these represent polystyrene, which is one of the components of styrofoam.